I'm Guido Bologna. Here is my paper, Transparent Ensembles for COVID Prognosis. So, uh, okay, I'm giving the outline of this presentation. So first, a brief introduction to the problem addressed here. The models used in this work, then I will summarize the experiments and some concluding remarks. So the purpose here is to explain machine learning models by propositional rules. In particular, here we focus on ensembles of machine learning models. This is a rare topic for rule extraction. Very often, rules are extracted for shallow multi-layer perceptrons. And here, the purpose is really to extract rules from several combined models. So in this work, what we have, random forest. I will go through the details later. Shallow trees trained by gradient boosting. Decision stumps, presenting a particular case of decision trees. And so ensembles of a particular neural network model, very similar to the multi-layer perceptron trained by bagging models used in this work. So we are using discretized interpretable multi-layer perceptrons, the MLP, that were introduced many years ago. The particularity here is that the first hidden layer, this is the first hidden layer, this is the second hidden layer, but here the connectivity is not full. Here we have full connectivity between those neurons and these neurons. Here also we have full connectivity. But here, between the input layer and the first hidden layer, each hidden neuron here receives only one connection from an input neuron and one connection from the bias virtual unit. Moreover, we have a generalization of the step function here, and this is staircase activation function. This function approximates the sigmoid function that we have here in the output layer or in the second hidden layer, this sigmoid. And this is particularly useful to extract, to know exactly where are the hyperplanes because of this small number of singularities. Okay, so now let's see a very simple DMLP neural network here. Here we just have one hidden layer. This is the hidden layer with a step activation function. This small network encodes a rule here, a propositional rule with two antecedents, x1 greater than t1 and x2 less or equal than t2 here. So how can we do that? You can see here the connection, the weight is 1 for x1 and the threshold for the bias is minus t1. So this encodes x1 greater than t1. For x2 less than t2, the 1 here is minus 1 and the threshold is given by t2 here. Okay, so this first hidden layer, its role is to obtain rule antecedents. And here, between the first hidden layer, okay, just this hidden layer and the output layer, we are doing a logical AND. So here you can see we have for those weights 100, 100, and 0 for the others. So this is a two-class problems. We have two classes, first class, second class. This codes the first class with 100 here, 100 here, minus 190 here. So here we really have to have those two neurons activated. perform the logical AND. So we have one here, when this neuron is activated, we have +1 for this neuron because of the step function. Also for this second neuron, so 1 times 100 plus 1 times 100, it's 200, minus 190, it's equal to 10. Then the sigmoid function gives this neuron to 1, and this second neuron is 0. The activation is 0 because of 0 weight here. Okay, so it's really a logical AND here, which encodes the activated antecedents. If only one antecedent is activated, so we have 100, the other is 0 here. 100 minus 190 is negative, so it goes to 0. So we really require to have those two neurons being activated to obtain this rule with the two antecedents. Okay, so we have spoken about the MLP neural networks, how we can do rule extraction after rule insertion. Well, this is for later. But first, let's see what is a decision tree, because we are using ensembles of decision trees. So a decision tree is a tree with nodes, and for each node we have a question. The question is equivalent to a rule antecedent. Is attribute A less than B? If yes, we go on the left side. Is B less than C? And so on. So we have the root and we have leaves. When we have leaves, so we perform a classification. For that leaf, we have A less than B less than C, and it will be associated to a particular class, for instance. Okay, so on the left we have yes, on the right we have no, and so on. And on the leaves we have what are the antecedents of a given propositional rule. Okay, so this is a single decision tree. When we have an ensemble of decision trees, you can see that we have tree 1, tree 2, here 600 trees. We can have many of them. So when we test a sample, we go on the first tree here, then we follow the path that activates the test sample. And we have prediction 1 here, we have prediction 2, and so on. At the end, all the predictions for the particular trees are averaged, and we have at the end the final prediction. So this could be simply a majority voting rule. What is the majority of the classes represented in the different predictions here? At the end, the majority class will win the classification for this test sample, and this can be achieved for the test samples. Here in particular we have random forest in this example, but it's an ensemble of decision trees. So now what is the idea here in this paper? The idea is to transform ensemble of decision trees, DTs, into ensembles of DMLPs, because we can generate rules from a single DMLP network, but also from ensembles of DMLPs. This was performed many years ago with those DMLPs network. Okay, so how does it work? So each path from the root to a leaf is a propositional rule. For instance, we have this rule here, we have this rule here, this rule here. So we can transform each rule into a DMLP network. This one goes to a DMLP, this one goes to a DMLP, and so on. And you can do this for all the trees of the ensemble. So at the end, all the rules extracted from all the trees are coded into a DIMLP ensemble, like this. Okay. So here, for instance, we have a particular rule. Here another one, so on. Here it's for a two classes problem, green, red. So the rule classifies a given class. The rule another class here between red and green and red, and so on. And all the classifications from the particular neural networks are then averaged in this layer. Hide 20 data set. And well, here we focused on a particular data set that was quite interesting with respect to the what is going on in the world with COVID. So the data set has blood samples from 375 infected patients by COVID virus in the region of 1. The data set was collected between January and February 2020. So blood samples for each patient. We have 74 attributes from which we calculate the average, the minimal value, the maximal value, because the patient stayed at the hospital many days. And so we have several blood sample in different days. So we calculate average, minimal, and maximal values. At the end, we have 224 attributes. So there are another 2 which are not here. Now, what is the proportion of patients who recovered from COVID? We have 201 patients, and the others unfortunately died, so 174. A more detailed description of the attributes can be found in this paper here, published by Chinese researchers in 2020. Okay, so the trained models are random forests. Random forests are ensembles of decision trees trained by bugging. Other interesting techniques are shallow trees trained by gradient boosting. Decision stumps are particular cases of decision trees. It's a decision tree with only one node. It's a very weak learner, but with boosting, it's interesting to have weak learners that become very strong after many particular stumps trained by boosting. Also, we used ensemble of DIMLP networks trained by bagging. So, very simply, what is the idea of boosting? So, the basic idea is to train weak learners sequentially, each trying to correct its predecessor. So, we train a weak learner, so he performs many mistakes, and then we try to correct these mistakes. Forest, DIMLP. AB is shallow trees trained by AdaBoost. Here gentle AdaBoost, and here is modest AdaBoost. Between brackets, here is the number of trees, 50 here, and also 50 DIMLP networks, 25, 150. This is the average train accuracy. Experiments here are run with 10-fold cross-validation. Between brackets here we have the standard deviations. So the testing accuracy here is given for gradient boosting. It's 96% on average. The best was here with 96.5 with general ADA boost for stamps. Sorry, for shallow trees. And so it's just the model. Then when we extract rules, if we take only account the rules, we see that the predictive accuracy is a bit different. For instance, here it's almost, here is 93.8, here is 96. Here, for instance, 96.5, here is 95.1, so it's a bit less, because the power of expression of the rules, it's a bit lower than the model itself. So, so this is the testing accuracy with the rules alone, but if we take into account the predictive accuracy of the rules when the rules agree with the model, it's even higher. For instance, here it's 96.9 with respect to here. What does it mean? Why do we have fidelity here? Fidelity is the degree of matching between the model responses and the propositional rules that are extracted from the models. Okay, so this is on the testing set. With respect to the training set, it's always 100%. So here it means, for instance, that for this one, that with 98% of the samples, the model and the rules agree. This is the fidelity by definition. Okay. So decision stamps trained by modest ADA boost produce the less complex rule set with good predictive accuracy. Our best result on average predictive accuracy was equal to 96.5%. And the average predictive accuracy of the rules was equal to 95.5. This was true when we consider the rules alone without the model. And also, we describe the particular rule set extracted from an ensemble of decision stamp. And overall, the extracted rules seem to be plausible with respect to the literature. You can find a discussion in the paper in section 3.6. Thank you for your attention.